paying me the big bucks to do analysis, but I end up spending query. Here I am on my PC and
fact is that the ability to couple the theory to background gauge fields, which have some within correlation. So topological means, okay, I can move them around. So that's also equal to UH UG, just because I have enough room, and then that UHG. And we have proven that UGH and UHG are the same. So the group is abelian. And then if you want the proof for higher D and higher P, well, it's just the same thing, but you extend with how many dimensions you like. So
Wix vous propose la puissance de l'IA pour créer le site dont vous avez besoin avec des fonctionnalités pour entreprises intégrées et un design sur mesure.
Asymptotic ODE. And this is essentially why these log corrections and other bad
Good morning, everyone. Thank you for coming in the morning. That's supposed to be the normal slot for the lectures, but okay. This course is the only one which is on Friday morning. I haven't slept so much, so I hope I will still manage to say something consistent. So at least here's the summary from the previous 3 sessions, where so each time I write the same thing, but now I write it a bit shorter, but I guess now you're familiar with the statement that we want to characterize what it means for a theory to have a symmetry, and we always have these 2 perspectives, background gauge fields for symmetry, which are topological. And in the first lecture, we said this statement for the usual symmetries, but then we generalize to higher form symmetries, which means that we have this number p here. It can be 0 if it's a normal symmetry, and then 1, 2, 3, and so on. What it means is the background gauge fields that you couple the theory to, they are now p+1 forms, and there is a generic background gauge transformation which is of this form. So you add to b the d of a field which is 1 less, and we say that the partition function has to be invariant under this background gauge transformation. And an equivalent statement is that there exist these topological operators which are supported now in codimension p+1, and since this is a group, when you merge them, you have a law that tells you how they merge, and they merge according to the group law. Okay, so we've seen this quite a lot, but the first 2 mostly. And then last time, which was this Monday, we saw that if you have a theory with a symmetry where there is an operation that is gauging, which produces a new theory. And now this theory no longer has this symmetry, now it's gauged. It has the gauge redundancy if you want to really insist on that, but it no longer has the symmetry. Maybe it has another symmetry. We saw some examples, and so sometimes you can actually gauge this new one and come back here. We saw this kind of Fourier transform. But it's really that gauging is a process that takes a theory with a symmetry and gives some other. And as an application of this, we looked at Young-Mills with gauge groups. And then when we say gauge group, we mean that we started from a theory with a symmetry G, and we have gauged it. And okay, we discussed, I don't remember if we really had time to discuss the theta angle. Okay, we don't put the theta angle. Theta angle was in these coefficients that we could add when we were gauging. You know, there was this ambiguity in the coefficients in the kind of form. And if you don't put anything, then pure Young-Mills theory has a 1-form symmetry. So this is in 4 dimensions. Pure Young-Mills in 4 dimensions has a 1-form symmetry which has this structure. There is an electric part and a magnetic part. The electric part is given by the center of the gauge group, and the magnetic part is given by the Pontryagin duo. Yeah, remember that if you have a group H, then I given by H hat is just the characters of H. And that's the fundamental group of the gauge group. So that's, I think, where we stopped last time. And so there was something I wanted to discuss that I will discuss now, but I want to announce what the plan is for today. So, okay, we are a bit late on the initial program that I planned, but it was kind of clear from the beginning. So I decided I should not try to rush. So we will see what we can do next time. But so today the plan is to comment on one more aspect of these statements, which I've been postponing until now, which is this anomaly question. So you see, these definitions are, there is this non-anomalous, which is here all the time. And so the goal of today is to get rid of that. It's always weird to give a definition of what something is not, like what a non-something is. So it would be better to just define what symmetry is. And so you already know, I said that if we remove that this is non-anomalous, what it means is just that we have to relax a little bit this equation. here there will be some additional phase, this times a phase. And in this equation, where this phase will be manifest in the fact that here there will also be a phase. So these equations will give both, but up to a phase. And that's fine. Why do we want to allow this? Well, it's because we are doing very hand-wavingly, we're doing quantum mechanics or quantum field theory, and a global phase doesn't matter. The states are defined up to a phase. And so this is a legitimate thing to do. And so that would be the goal of today, to get rid of this non-anomalous on this side. So this in itself is not so hard. Just done it. That's fine. But the problem is really the interaction with what we did last time, which is the gauging. Because here non-anomalous was absolutely crucial, and here I cannot get rid of it. And I think I mentioned, and I will mention again, why. You remember that one phase is not a problem, but then when you gauge, you sum over the partition function with different phases. Right? There was a mathematic formula Z, the gauge partition function was normalization, and then there was a sum over all the BPs, or the classes of BP plus one. We should discuss a bit with the details of this. Schematically, we have this, and then we have the partition function of the ungauged theory coupled with the one, maybe times some other thing. But okay, crucially here, you see that if now I make a gauge transformation, the class doesn't change, but now the representative here, with a gauge transformation, this will pick up a phase, and now I sum. And so the phases might interfere. And so that's why the gauge theory doesn't make sense. You cannot gauge if there is an anomaly. So, but then there's a conflict, because at the beginning I said, so you also remember the very first point that I made at the beginning of the first lecture, the goal was to generalize the notion of symmetry. And how do you know it's a good definition? Well, it's a good definition if you can do what you are used to do with symmetries. And in particular, you still want to gauge. So somehow we want to salvage this thing. So we will not be able to gauge an anomalous symmetry, but we want to be able to gauge, maybe you have a big symmetry, G is a symmetry, but maybe it contains a subgroup, H, which is non-anomalous. Right? What would it mean? It means that if I put all of G, I have these phases, but maybe there is a subgroup for which the phases are trivial. And now that guy would be non-anomalous, so I can definitely gauge this one. Engage the non-anomalous subgroup. But then, what's the resulting thing? What about those guys in G, which they were part of a group, they were very happy. It was an anomalous group, but they were happy in the group. And now, some of the group has been removed. A whole subgroup is removed because it's no longer a symmetry. So what remains? So that's what we are going to discuss today. The plan for today is basically discuss the anomaly. But before that, in 15 minutes, I just want to finish on what we said last time with young mates. Right. So just one thing, I don't remember if I really arrived at this statement last time, but I definitely drew these examples with SU2 and SO3. So the difference between those two groups are exactly this. So one has a center, SU2 with a V2 center, but it has no fundamental group. And then SO3 is the opposite. No center, but it has a fundamental group. And I showed last time, well, still there, you can see those. think this is the diagram for last time when I drew the charges of the line operators, the electric and magnetic line operators. This is triggered, and in the SU2 theory, we had Wilson lines and no Tooth lines, which would sit here. And in the SO3 theory, they're still there. It's the opposite. We had the Tooth lines and no Wilson lines. And these lines, they can serve as a diagnosis of the phases of the gauge theory. And so that's one thing. So again, I want to briefly comment on this. So what is the fate of the one-form symmetry? One-form symmetry, so that's a then, as always with symmetries, it can be maybe only approximate, or it can, under the RG flow, if there's pure Young-Mills, what would happen, but maybe you have some matter content in the theory, and then you can ask in which phase of Young-Mills. And you probably know this story, that in order to know in which phase you are, you look at the law, the area law or perimeter law for the Wilson lines, for instance. And so we can reinterpret those things in terms of one-form symmetry, whether it's spontaneously broken or not. So this is an important thing. So let's just recall what it means for a usual symmetry to be spontaneously broken. So if we have an ordinary symmetry, that's where we go. So for ordinary symmetry, we set the definition. We say that an ordinary symmetry, G0, is spontaneously broken if there is an operator, a charge operator, O, because it's a zero-form symmetry, it's a local operator, so there's a charge operator O. O acquires a vacuum expectation value. That's spontaneously broken. So which means, okay, the symmetry is there. It's a symmetry of the equation of motion, but in the particular vacuum in which you are, there is a charge here as a there. So the vacuum breaks the symmetry. And so that's the most straightforward definition. And it turns out there is an equivalent way of looking at this, is to look at the correlator of two charge operators with opposite charges. So we take this one and the adjoint. So if you take this, O conjugate X and O Y, it's a bit easier to work with this because then that's the product operator is neutral under the symmetry, but then you can look at the long distance and look at what this goes to when X minus Y goes to infinity. And then you can ask again, does it go to 0 or to non-zero? And then by locality of QFT, if it goes to something non-zero, it means it's equivalent to the operator to have a non-zero there, and if it goes to 0, it's equivalent to the operator. 0. So you can also check if the symmetry is spontaneously broken or not by just looking at correlators of uncharged, globally uncharged operator, but supported at 2 different points. And the reason I'm saying it this way is because I want to make a parallel with the higher form. You see, what is an operator supported at X and Y? So 2 points which go very far, and one of them is as a dagger. A way of saying this is that O is supported on an S0 sphere. S0 sphere. The sphere of dimension 0 is just 2 points. And then you make the radius of the S0 sphere to be very large. And you look at the behavior of the operator supported on the 0 sphere when the radius is large. And so that definition allows to generalize to P-form symmetry. So we can define that GP is continuously broken if there exists a chart operator OP such that the similar statement to this such that the of OP now supported on ST of radius R goes to non-zero when R goes to infinity. That would be the most naive generalization of this. The problem is this is not really well defined because operators can always be redefined. You know, you can have you can redefine operators, and so this statement will not really work. And actually, if you know where we want to go, we want to say that for instance, that if the Wilson line has a perimeter law, which means this grows like the exponential of minus the perimeter of the loop, you want to say that the symmetry is continuously broken. But exponential of minus the perimeter goes to 0. So actually, we cannot really write this. So let me write something a bit approximate. So if this goes to does not go to 0 too fast when R goes to infinity. So now that's a very vague statement. So does not go to 0 too fast. So if it goes to 0 very, very fast, then we will say that it is preserved. But if it does not go too fast to 0, then it is continuously broken. What does not go to 0 too fast mean? I don't want to enter into too much detail, but basically it means that you can find some redefinition of the operator or add counterterms such that it does not go to 0. So it might go to 0, but it should not be too severe. And then, okay, so I say this, and I cannot be really more precise because then you have to redefine it for each P. But for what I mean here for when P equals to 1, it means here. Equals to 1. So now we are looking at the expectation value of a Wilson line, or a line in general, actually, not necessarily a Wilson line, but let's say we have Young-Mills with G simply connected, so we don't have this, just have a center, so we have the center symmetry. Then we have the Wilson line on an S1 of radius R. So you just have a big loop. And then it can behave like e to the minus a number times the perimeter, P, so basically R, or like number times the area, so R squared. And so if it's this first one, that corresponds to spontaneous symmetry breaking, while if it's the other one, it decays so fast that it's
Sorry, what is the other one? What is the second case?
this is area law.
Okay.
Again, the goal is not to discuss the phases. I mean, you've probably seen this. I'll make some calculations like this. I just mentioned this because this was used from I think the 70s probably to check if a theory confines or does not confine. So actually, the interpretation is if you have an area law, then there is confinement, and the argument is what is the expectation value of a Wilson loop on a very large circle? Well, you can make it so that the Wilson loop is actually something like that. It has a length here, say r, and t, so you extend it into space and time, and then this probes the potential that is exerted between two probe particles at a distance r for a very long time t. And then basically, if you have perimeter law, it means that v of r, so, area law basically means that v of r grows like r, proportional to r, so that the area of this is t times r, while perimeter law will mean that v of r is it can grow also, but let's say constant or 1 over r, let's say constant. And so that's confinement. And that's maybe either Higgs phase if V is constant with a Higgs. So if you're in the Higgs phase, for instance, you have a Higgs mechanism that breaks your gauge group at low energy, then the gauge group is no longer there, so there is just no force. So then V constant, no V. Yeah, so these were the things that were said in the 70s and 80s to diagnose if there is confinement or not. And what I say is that all of these things can be rephrased now with the language of these one-form symmetries and whether they are preserved or continuously broken and so on. So let's just give some examples. Make this concrete. Right, let's give 3 examples. One of them is the pre-Maxwell theory. So in Maxwell theory, we saw 2 weeks ago, the symmetry is U1 electric times U1 magnetic. And what's the fate of the symmetry? Well, of course, you know that in Maxwell there's no confinement. So here you can compute everything explicitly. It's a free theory. So if you compute the expectation value of a Wilson line or 2 lines, you find that there is area law, perimeter law. For Wilson and Luft loops. Which means that both these symmetries, they're actually spontaneously broken in the vacuum. And both are spontaneously broken. And then you have the analog for higher form symmetries of Goldstone theorem. If you have a continuous symmetry which is spontaneously broken, then there will be some Nambu-Goldstone boson for that. And the Goldstone are, what's the Goldstone boson? It's just the photon. So the photon is a Goldstone boson for U1 magnetic. And then you might ask, okay, there's also U1 electric. So what's the Goldstone boson for U1 electric? Well, that's you apply electric magnetic duality. So that's the dual photon, the field that you would get by dualizing. And that's the one which, so this is pure Maxwell. But then if you do QED, in QED, we already discussed, maybe I can just write it. In QED, we add fundamental matter. Yeah, I didn't put in the reminder from last time, but there was another important thing, which was this screening thing. And the fundamental matter, you know, in QED, it screens the Wilson lines. So Wilson lines are now screened. There's no longer the symmetry. So the symmetry is only U1M. It's only this. So, and there is still, which is still spontaneously broken. And therefore, there is still the photon. So indeed, QED is still there. But you can no longer dualize it, because these charged fields. So the dualization process doesn't work. Dual photon. Right, so these were for the abelian theories. You can also consider abelian, just to go through all the models. Abelian Higgs model. So in the abelian Higgs model, you have QED, and then you have some fundamental matter, but now it's not matter, it's a Higgs boson. And this Higgs boson can acquire Vev now, it's a scalar field. And if it acquires a Vev, it can break the gauge group. So then, again, because this is charged, we have just U1M. And now there are two phases, whether you are far above or far below the Higgs mass. And so there are two phases. The phase where it is spontaneously broken, and the phase where it is unbroken. When it is spontaneously broken, you have you're in the Coulomb phase. This is the Coulomb phase. And then when it's unbroken, you're in the Higgs phase. Hence the name. If you have the photon, so these are relatively simple things. Again, these are abelian theories, but it's just to put all these things into the framework of these generalized symmetries. And the last theory that I want to look at is Yang-Mills. And in Yang-Mills, it's a bit more non-trivial, even though the statements that I will make here are not so complicated, but let's give it help. So for a long time, there was this puzzle. It was known that Yang-Mills, in Yang-Mills, there is confinement. And so there is a phase, which is confinement. And then if you add a Higgs boson, then below the Higgs scale, there is no longer confinement, the opposite. And so the question is, what is the nature of this phase transition? What is the order parameter? And the problem is the symmetry. If you go back to the Landau paradigm, the phase transition should be characterized by some symmetry, which should be spontaneously broken or unbroken. And the problem was that there is no, in the standard sense of symmetry, there is no standard order parameter. So people actually realized that what you should look at is the Vev of these extended operators. So in a way, you could say that they already understood that you needed to extend what symmetry was, because you need to you need to extend the notion of charge operator. And so with this understanding, if you have, say you have SUN, Young-Mills, there is a one-form symmetry. So this time, even in pure Young-Mills, remember, so here pure Maxwell has these two symmetries, but pure Young-Mills has only electric, right? Because when I just erased it, there is only the center symmetry. There is the end, one-form symmetry. That's it, one-form symmetry. And then it can be, again, at high temperature, it can be spontaneously broken. And then at low temperature, it is preserved and broken. And so that leads to confinement. While here, there is no confinement. There are fluids floating around. And in between, because there is a symmetry argument now that separates these two phases, there can be indeed a phase transition. And so very hard to probe analytically because we are in Young-Mills. And but there is a phase transition. Which has all the, which you can study, for instance, on the left. What is the order of the phase transition? Yes.
From that point of view, it looks like the behavior of the phase transition for SUN, PSUN, for the one-form magnetic, is very different.
Yeah, well, yes. Why do you say it looks very different?
Because in one case, the operator, which is the order parameter, will not be the same.
Yeah, it would be indeed to be the.
And it doesn't have this interpretation that was massive. Wow.
But it will be massive monopoles. But yes, indeed, if you are in PSUN, you cannot, means that by definition you cannot put quarks, probe quarks. They would not. So yes, indeed, it is very different. Okay, so and in this, so yeah, this is confirmed by lattice computation. And then the comments, last example in this list, now here, if you're not in QED but in QCD, so QCD is Young-Mills plus fundamental quarks. Fundamental quarks break the symmetry entirely, so there is no symmetry at all that remains. No one-form symmetry. Hence, if you believe in this generalized lambda paradigm, the indication is that there cannot be a transition, no phase transition. So the statement, if you believe in the symmetry argument, is that in pure Young-Mills, there is a phase transition between confinement and unconfined phase. In QCD, as soon as you add quarks, there is no phase transition. Of course, if you can have an approximate one, for instance, you add very massive quarks and then you go at very, very low energy, far beyond that, then this will be an approximate, very, very good symmetries. There will be something that really, really looks like a phase transition. But if you look at scales which is large enough, you will not find it. And indeed, this is also in agreement with lattice gauge theory computations, that even though it seems that there is a confinement and an unconfined phase, it's a bit like in real materials, you have liquid and gas. There is a phase diagram, you have thing like that with a critical point, and so you can go from liquid to gas going around here without never having any non-analyticity in all the thermodynamical parameters. And so the same is conjectured to happen here, and that's the symmetry argument for it. which is again supported by numerical computations. So maybe you're wondering why all this. It seems so powerful. Maybe we could we claim that we have solved the Young-Mills mass gap and confinement problem. The thing is, it's slightly different. There is a confusion about what confinement means. Here, confinement is defined by the potential to have this kind of law. It's slightly different from color confinement, because of course in QCD, as law, there is a kind of confinement. There is color confinement. You observe only gauge invariants, so like white variants or mesons. You never observe individual quarks. So in that sense, quarks are confined. And so there is the mass gap, but it's slightly different from this definition here. So that's the first thing. And then the second thing is, of course, this is not a proof. This is an indication. We have identified some symmetry, and then we say phase transition are associated to symmetry breaking or not breaking. And but it is not a mathematical proof. That's why it doesn't solve the official Young-Mills problem. I don't think. Well, maybe one last comment, and then I should really move to today's topic. The last comment here is that the center symmetry here was identified also as a center symmetry in the 70s or 80s, and the argument at the time was you can compactify Young-Mills, so this is 4-dimensional Young-Mills. You can compactify it on a circle times R3, so this would be R3. Say you're in Euclidean, this is S1, radius R. And then you see the charged objects, they are these Wilson lines, and they can either wrap the circle or not wrap it. So if they wrap the circle, you put them on the circle, then from the 3-dimensional perspective, they look like a point, and they can also be extended in space, in that direction. And so with this interpretation, you see that with Dn, one-form symmetry, when you compactify on this, it descends to two symmetries, actually. There is now a zero-form symmetry, because from the point of view of R3 in 3 dimensions, there are now charged local operators, so there is a Zn 0 and a Zn one-form symmetry. And the point is that this one is now usual symmetry to which the standard arguments of symmetry breaking can be applied. So that's the one that was called a center symmetry. And the loop. So what generates it? Well, it's just a Wilson loop that's wrapping the circle, and then that's what's called Polyakov loop. But again, from the modern perspective, it's just the Z acquired by Polyakov loop. It's just the zero-form symmetry that descends from the one-form symmetry when you wrap it compact. So yeah, so that's the one that controls the confinement or unconfinement transition. This one is always important. Okay, are there any questions about this? Because then I will move to anomalies. Okay, great. So now now we go back to our challenge, which was to define anomalies and to understand how to gauge theories when there are anomalies. And my strategy for those lectures, as you could see, was to always try to use simple examples, the simplest in which the phenomenon occurs so that we have a good intuition and then to generalize. And if you remember the first lecture, we had the pre-complex field. Then in the second one, we had the compact real. So that will be, again, our starting point. This is incredibly useful. Also, last time we saw that actually it's quite similar to Maxwell, even though it looks much more complicated, but formally these are really very similar fields. So let's go back here, and let's see that even here we already have an anomaly. So all the phenomena that we want to see will appear here. So let's just remember what it was. So we had the action. So our field I call phi. Last time I was careful about putting the right constant, but okay, here let me just write 1/2. The action is the integral over mv. We are still in d dimension, and the action is 1/2 of d phi the action, and crucially phi is identified with phi plus 2 pi. That was the first thing. And we have discussed several times that there are two symmetries. There is the winding symmetry and the momentum symmetry. Both are U1. U1 momentum is a zero form symmetry, and then U1 winding is a d-2 form symmetry. This is actually the example I used to motivate the fact that they are higher form symmetries. And the background gauge fields are the momentum, which is a 1 form, and the winding, which is a d-1 form. Everything clear? So that the associated currents are J1 momentum. This is at d phi, and J winding d-1. This is star 1 over 2 pi. Good. So, okay, so we've already studied this, and then we claim that there are these two symmetries. So, as per our general definition, there should be a way to couple the theory to these background gauge fields. And the way to do this is quite straightforward. Just add them, integral 1/2 that's the kinetic term. You enforce that it's invariant under transformation. So the transformation is phi 0. So remember that momentum is associated to the shift symmetry. So it's very right. Phi 0 plus some shift, which is lambda 0. And then the m shift as dm plus the lambda 0. I call it m because it's the one associated to m. And so clearly both terms are invariant. Now the other guy, winding, d-2, shifts -1, shift with a lambda winding, d-2. Now how can I couple it? We discussed this. You always write a coupling with J, with star J. So there will be no star here. So the coupling is naturally plus I over 2 pi integral of g. I'm still in the integral d phi minus b, and with d1. so this is the coupled action. The most natural thing you can do, of course, as I said, there is some ambiguity. So if you want, you can add any term which depends only on dB, only on dBm, dBW, some combination of those, and also some other counter terms. So for instance, here you see there is this term that has appeared, dm, dW. You might want to remove it, but we will see that it has consequences. But this is the simplest thing we can write. We say that all the d phi, they are now accompanied with dm, and the d phi should also wedge with dW. So then that's the most natural thing to write. The problem is, as you might see already, is that if you set one of the fields to 0, then it is gauge invariant, but globally it's not. So under a full gauge transformation, this is not invariant because of this term here. So if you compute under this, these are the background gauge transformations, then delta S is I phi G phi minus B, which this one varies with the theta. And so this is non-zero. So you might want to try to fix this, but there is no way. Again, so here it depends only on lambda W. So you might want to add something which depends on lambda W that kills this. But then the only way to remove that would be to add some other term, but then there will be a non-invariance under that one. Right around. There is no way to get rid of this. So actually, the symmetry U1 M U1 is anomalous. So now we have a perfectly fine theory, some perfectly fine symmetries, but still I hate anomalous. So I should answer now some FAQ, frequently asked questions. Let me. Yes.
You said that so if I set B magnetic to 0, then it is invariant?
So if no, wait, okay, this term is not. If I set B magnet to 0, yeah, we can see it's not. But then what I say is that if we decide to never turn on B magnetic, there should be a way to make that one alone. So let's see, do this. Yes, because this is always, actually, that's a good question. I already answered it last time, but that's, I again forget. This is delta S, so actually, this was my next equation, so let me write the transformation. So V of, I write globally B plus D lambda. So this is a shorthand for S, for Z. So Z now depends on both of them, so M and W. And W, I can write this, is equal to Z of B times the exponential of this term here. And then I think we discussed last time that because of the quantization thing here and on the parameter, there is this thing, integral d pi over 2 pi with d lambda over 2 pi times 2 pi I. That's an integer, and so in the exponentiated action, this gives a 1. So actually, that term here does not contribute the anomaly. So the anomaly is not the non-invariance of the action. This, we discussed last time, can be reabsorbed. It's really in the partition function. So Now I write the phase properly. TV. So that's the conclusion of this complication. This is, we should always look at the partition function. And the claim is there's no way to get rid of that. So okay, that was my. So first of all, if we can get rid of the phase, this means it's equivalent to there is actually no anomaly. So the anomaly is really, it's more than the fact that there exists a phase, it's the fact that there exists a phase and there is no way to remove it. We will see a bit more concretely what it means mathematically. I can just say it already, that group cohomology. Group cohomology is the technical tool that says what it means for it is not possible to remove. That's the first point. The second point is we have used those symmetries for 2 sessions now. And what does it mean? If there's an anomaly, does it mean that it's bad? Is anomaly symmetry still a symmetry? Still a good symmetry? And the answer is yes. Perfectly good. And we will demonstrate it today. The reason why it's good is because all the properties that we want to give to a symmetry will still here. It's a matter of definition.
What is the difference between an anomaly and the transformation of the symmetry at all? Right? And phase when you transform the partition function.
Yeah, that's okay. So if you have a transformation which is not a symmetry at all, then in general you will not be able to write it this way. So here, okay, yeah, here is the phase, but it's the phase that depends only on the background gauge field and on the variation, the gauge parameter. In general, if you have a non-symmetry, if you try to write this equation, here you will have some dynamical fields. That's the slide that here it depends only the phase, it depends only actually this thing I will call A or anomaly, and it depends only on B and on lambda, but not on any dynamical.
When you say lambda, you mean the lambda associated to the background gauge field, or also
Yes.
can it depend on the lambda associated to phi?
Well, the one associated to phi is the same. So here globally there is a so okay, here the symmetry is U1 times U1, but I can consider abstractly it's just a group, and I have lambda for that group, which will product a pair of 2 things, lambda m and lambda w, and these are the lambdas that are. But it does not involve phi, which is my only dynamical field. So in the gauge theory, you should never have a gauge field. Actually, this is a good point because we will see just in a minute. This was my next point. If you try to gauge, of course you could naively gauge, but then you would have a thing like this, where here you would have dynamical field, like the gauge field that would arrive here. So that's not allowed. I will show this in a few minutes. Yeah, so then to answer another question, if so is it still a good symmetry? Well, first of all, we can look at the symmetries individually. U1 momentum, is it still a good symmetry? Well, yes, because as you can see, that thing, I've written it in a way that it does not depend on lambda momentum. So if I vary only with the momentum lambda, then it's invariant. So then it's non-anomalous. So U1 momentum is non-anomalous. What about U1 winding? It's also non-anomalous, even though here it seems that it depends on lambda. But then I could add a counter term which will put the phase somewhere else, and then the theory will also be invariant under lambda winding. So two comments is that U1 M or W are non-anomalous individually. And you see the anomaly only comes from the interaction between them. So that's what's called a mixed anomaly. And also I should say that this is all this, what I call anomaly here is known as tooth anomaly. It's a mixed tooth anomaly. Mixed, which means the full group U1 times U1 is anomalous, but it has subgroups which are not. And that's exactly the situation that I described at the beginning. I said, what if we have an anomaly, but there is a subgroup which is non-anomalous, then certainly we can gauge it. So here it means that if I want, I can gauge U1 or U1W.
Both of them, or one
No, not
or
both.
the other?
No, both, they have the anomaly. So I can gauge one or the other,
You have to
but
choose.
not both. And then the question is, what happens when I gauge that? So here it's a simpler case than the general case that I mentioned at the beginning, because the full group is just a product. So in a way, you have a product, non-anomalous, the global thing is anomalous. If you gauge one part, then I asked at the beginning, what happens of the rest? You had a group and then you have removed some elements. But now what remains is still a group, right? Because it was a product. In general, you could what remains is a quotient. It's not or even something else. So in general, it will be complicated. In this particular case, because it's a product, it's a bit of a simpler situation. But that's why I'm starting here. So that's the next anomaly comment. The other comment is about it's kind of the same as here, but in another perspective. Is anomaly a bad thing? It looks bad because the word anomaly is something is not working right. It's not normal. But actually, no. Nothing is bad with it. It's just it's anomaly. So we could look at the history of particle physics to see where the word anomaly comes from. Of course, it comes from there were some expectations in some particle experiments, and then some of the experimental outcomes were not in agreement with the expectations. So this was an anomaly, and that's where the name originates from. And then it was later discovered that when you have gauge theories, and if you say mistakenly that there is the gauge group is a symmetry, and then you ask, oh, the symmetry maybe it can be anomalous, it can have an anomaly, and then if this is the case, then that's a pathology of the theory. So, and indeed, that's just is a modern way of saying things. It's just what I've already said several times, that if you have an anomaly, you can just not gauge. So of course, if you have already gauged and there was an anomaly before, then it's bad. And the anomaly is bad, it's because for a long time, people tended to focus on the already gauged here. So that's okay. Next comment. And the next comment is, I'm doing things here with the compact scalar. There is an analogy between compact scalar and Maxwell. It's exactly the same. You replace all the zeros by ones and you get Maxwell. And so everything I said also holds for Maxwell. So that's not really a question, but the question could be, is the same holding for Maxwell? And the answer is yes. So there is a mixed electric, magnetic tooth anomaly. And all the formulas are basically the same. You just put all the zeros become 1 and the 1 become 2, and that's the formula. So, yeah, then another question is what about chiral fermions, spin-offs? Sometimes the anomaly is supposed to be related to the presence of chiral fermions. And indeed, you know, when you write the path integral with chiral fermions, then you have the measure, which is not invariant, and that produces an anomaly. That can be the source of the anomaly. But here, there is no such thing. There's no fermion at all, no spin. So how come? Well, the answer to this question is very simple, is that indeed, those guys, they can imply some anomaly, but that's only one way of getting an anomaly. There might be many other ways. Actually, I just shown one without. So if you have those, then indeed you have to compute their charges and so on, and it might lead to an anomaly. Sometimes it doesn't, sometimes it does, but definitely it's only a one-way implication. You don't need to have chiral fermions or non-invariance of the measure to. The fact that anomaly is due to those was at some time, I think in history, very deeply rooted in the mind of people. And so one of the main applications, actually, why is it called tooth anomaly? It's because the realization that global symmetry, so non-gauge, can have anomalies, and this is not bad, is probably due to tooth. And he actually said that it's not only not a bad thing, but a very good thing. It's good because there is anomaly matching. What is anomaly matching? It's the fact that this anomaly, as we will see, because it's characterized by some group of homology, which is often a discrete data, it cannot jump. So if you have an RG flow, what happens in the UV is still there in the IR. And the argument at the point, and that shows how much the idea was linked with the fact that there were these fermions, is, I mean, it's still a valid argument, of course, is that if you have a theory with an anomaly, you can always imagine that it is coupled with a bunch of very weakly coupled chiral fermions, which have exactly the opposite anomaly, so that the full thing is non-anomalous. That's what happened in the UV. And then you go along the RG flow, and then in the IR, those guys didn't do anything, so their anomaly is still the same, and so the anomaly between the UV and the IR has to match. Basically, you couple, but very weakly you couple the fermions and then you remove them. But in fact, we don't even need to do that. We can just characterize the anomaly like this and say that it is matched along the RG. Okay, so these are all the general comments that I wanted to make about anomalies. And now, soon. Okay, before that, I don't. Do you want the break now? When did we start on time?
1 hour ago.
Then, okay, then maybe let's have a 10-minute break. So then the plan is to discuss some examples of anomaly in quantum mechanics, so even simpler than that actually, and then to characterize them using group cohomology, and then to finally answer our question: what's happening when you gauge? So let's see in 10 minutes. Okay. Donc, yes. So, I promised I would illustrate with some basic quantum mechanics examples, but I think, given the time, actually, I'm not sure I will talk in detail. I have some detailed examples in quantum mechanics, but let me start with the drawing that I had at the beginning to characterize the anomaly. So again, as you know, we are free to move between the background field representation or the symmetry defect, and some arguments are easier with that, so let me do this. So, you know, the general thing is that UG prime becomes UGG prime. This is without the anomaly. And now if we have an anomaly, we have a phase times e to the I. And then this phase that I denoted by A here, I will just, in this language, just write it as omega of G prime. So let's assume I have this. And I want to look at this from the point of view of quantum mechanics to just illustrate what the link with this group cohomology and see how this is related to things that are very familiar. So quantum mechanics in the language that I'm using here is d equal to 1. Right? It's QFT, Euclidean QFT in 0 plus 1 dimension. If you want, you can weak rotate back to Lorentzian, which would be more natural from the point of view of mechanics, but it doesn't really matter. So d equal 1 means that actually this drawing, I can draw it in a simpler way. So now that's all that's my one-dimensional manifold on which my quantum mechanics is defined. It's basically the time axis. And as we discussed, I think last time, the fact that we have symmetry operators, now they are points. This is UG, supported at this point, and this is UG prime. The fact that they are topological means that I can freely move them in time. They commute with the Hamiltonian. That's what being a symmetry is. And now what I'm saying is that if I have this configuration where I have UG and then UG prime, it's the same as the configuration where I have just UGG prime. Okay, so maybe I should put the prime here, because I'm first with G prime. This times exponential of I omega. That's what it means here. In other words, we have what we also discussed last time. Here we have a zero form symmetry that acts on zero form. Yes, okay. Last time, remember, we said that p-form symmetries act on p charges as representations of the group. Here we are everything is zero, so we have a zero form symmetry which is supported on these local operators. It acts on local operators, so maybe there is some O. There's O here, and then if you remember, how does an operator UG act on O? Well, you put it on a sphere that surrounds O, but here a sphere is just 2 points. So you put UG over here and UG inverse over here, and you sandwich it. That's the action. That's G acting on O. And last time we proved that this is a representation. O transforms in a representation of O. Kind of put it. And indeed it still holds, because if you act with G and then with G prime, well, you might get this phase. You might say, oh, I can first act with G and with G prime, or with GG prime. But you see, because this is just a phase, and you have something here and the inverse, it just cancels. Yeah.
Is the statement that the phase depends only on G and G prime equivalent to the statement in the other formalism that A depends only on B and delta?
Yes, I would say so. So here, okay, I want to connect with this. So we have to remember the first time that I did the translation very explicitly. We can assume that B is 0. we are in a trivial background, and then those guys are just different lambdas. So you remember we had this thing with the theta function. So this is a profile of lambda where it's 0 here, and then it jumps by this and this. Of course, this is I'm assuming that now it's a U1 symmetry to have lambda. So it jumps by this. So there is a step, and here that it jumps both at the same time. And the transformation between this lambda, well, maybe I can say this is a B, and then there is a lambda that transforms from here to here, which adds another thing. And so indeed, B and lambda contain all the information. So this is the same as B and lambda. So we see that G, so even with this, so let's assume that we have this. So G, we have a 0 form, acting on operators that acts via representations. Not projected, there is no place. G acting on G prime, acting on O, is equal to G prime acting on O. With this drawing, even combined with this, yes, is acting on operator. But then, when acting on states, so what is acting on states? The states, I will come back to this. The states, they are associated to the boundary of your manifold MD. The boundary is like a point. And here there is an endpoint. There is a state here. It's still the same state. If you act on the state, then you act only from one side. And that's where the phase arises. So when acting on states, we have a projective representation. Projective because the action of G and then G prime is not the same as G prime. There is a phase which is given. So now let's look at the consistency condition that the phase should have. Not every phase here is possible because you still want to have some notion of associativity, but you might not want that maybe. But let's say that we want this. Again, this is we are defining something. So we say that we want this phase to satisfy an associativity thing, which is which means that only the topology changing, like locally topology changing events can create something. Okay? So 2 points is topologically existing from 1 point. Right? The number of connected components has changed. So there is a topology action that happens, and that's the only thing that can happen with points. So the phase we claim can only happen when 2 points merge into one. But then when I have 3 points merging into one, I can first do two. I can do it this way: 2 merge into one, and then the third one merges, or I can do these 2 and then this one. Yeah. So we want this to be associated. So what is the condition that we can? Here is that. So if you do this, let's draw it in the line. Let me not write U each time. I just write the G. I have G, G prime, and G prime prime, and I act. So I first act with G prime. Actually, I can do it. I can do it with the. So this is the same as G, and then G prime, G prime, G prime prime, with the phase G prime, G prime prime. Let's call them 1, 2, 3. 1, 2, 3, 1, 2, 3. 2, 3, like that. And then I have G1, G2, G3. I have the other phase. So I have acquired the phase G1 with 2, 3. Plus. Okay, that's what we get doing it this way. But then we could also have done it the other way. First merging 1 and 2. And then the third one, G1, G2, G3 times e to the I. Now I merge those two, so I have omega of G1 G2 plus omega of G1 G2 G3. And we want these two things to be the same. So imposing that these two are the same means that we have this equation that holds G2 G3 minus G1 G2 G3 plus G1 G2 G3 minus G1 G2 equals 0. And just reorder the terms. So that's the condition that we want to impose on the omega. And then the second thing that we said is that anomaly is there if you cannot get rid of the phase. And there is a way of maybe getting rid of the phases. There's a trivial way. So imagine you have a group with no anomaly, and then you rescale this by a phase that depends on G, this one by a phase that depends on G prime, another phase, and those things don't add up, well, then the product will have a phase. But that's a fake phase. So this we want to not consider. So we want to get rid of phase redefinition. So if I call this phase that I add to each of the three G's, I call lambda of G, then we want to say that omega of G1, G2 should be considered the same as omega. Let's say I should say that that function should be considered the same as omega G1, G2 plus anything lambda that depends on G1, G2 minus lambda of G1 minus lambda of G2. That's yes. Did I make a? So lambda is a function of one operator, which is just the rescaling. And then you see, if you rescale by, there is a plus here and there's a minus here because it's on one or the other side of the equality. And so these two things should be considered the same. And these two statements, so anything that satisfies omega, satisfying the first one, modulo the second one, that's exactly the statement that omega is in the second group cohomology of G with values in, there's always an ambiguity, like you say U1 is the exponentiated thing, or R, and let me just write U1. Technically R to pi Z, that's just the additive version of U1. So we see that we have different ways of characterizing this. There is projective representation, but genuinely projective. The projective that cannot be rephrased as a non-projective one, or anomaly, or element of this second group cohomology. These are equivalent characterization of the anomaly in one dimension. So I could give a definition of what this is. So let me have it. Then I will give some examples. Yeah, for those who don't know, because with some of you I've already discussed those things, but you can try to think of a quantum mechanical system which has an anomaly like this. So you can think of it either in these terms or in terms of projective representation. Yeah, so just the definition of group cohomology. So we take G to be a group. Then in principle, I can define, let me just say it orally, Hn of G with values in, but it can be quite general. The most general thing is that M here should be a module, a G module, so it means some space on which G acts. The important thing is that G acts on that thing. And this is, if you put M here, then the different cycles, like omega, they would be valued in that thing. For physics, like to deal with all of those things, we don't need a general M, we just need to have U1 or R mod 2 pi. Let me put U, let me put R pi z. You can also replace this by U1 if you want, then it's just that the writing here, every plus becomes a times and minus becomes division, so it's a bit less easy to write. So I want to define only those things. And then, as I said, in principle, the group acts on here, and you might ask, how does it act? Well, I declare that it acts trivially. So G acting on an element here is just that element. So I will forget about this action. So because of this, the group cohomology now depends only on the group and on the degree. So what is the group cohomology? Well, as usual, you define the cochains. So Cn of G. This is just the set of all functions from G times G n times into our target. So for instance, omega. Our omega there is a function, takes two elements of G and it outputs some number modulo 2 pi z. So that's an element of C2. So these are the cochains. And then there is a boundary of some differential, let's call it delta, which goes from Cn to Cn plus 1. And what does it do? Well, if I have an omega, which is in Cn of G, then delta omega, it should be an n plus 1 chain. So this should act on n plus 1 group elements. So then G1 up to Gn plus 1. What is this? This is defined to be. So to remember this, there is you can imagine a little train where there is one character per car, but then there is one more person than the number of items. So then there's always one which has 2 persons, and that person goes around the train. So first you start with the first guy not here. So you write omega evaluated in G2 up to Gn plus 1. That's fine. These are NGs. And then the G1 enters train from the left. So then you have omega G1, G2. That's a product. And then G3 and all the others. And then because G2 is not happy to have G1, G2 goes into the next one. Then you have omega of G1, and then G2, G3, and all the others, up to, at the very end, well, the last guy, n plus 1 is kicked out. So the last one is, we just have G1 up to Gn, and no product. So let's count how many terms we have. We have n plus 2 terms. Right? And then we put alternate signs, so minus, plus, and so on. And then here there is a plus minus 1 to n plus 1. That's the formula for the differential. And this is so that you can now check that if you do delta twice, you get always 0. So that's a good operator that will allow us to define cohomology. And you can recognize that here, the first line is exactly delta omega for omega. So if n equals to 2, what is delta omega? It's this. The train, there is 2, 3, then there's 1 which enters, and then there is 2 and 3, and then 3 exits. That's the way to do it. And if there was an action, the more general definition, when there is an action, we won't need it for that discussion. In principle, we need it later, but I don't know if I will reach that. If there is an action of G on that thing, then the action happens here. So here, if you read the more general definition, there is actually a G1, which is here before entering the train. G1, it acts on that thing, which is an element of that. But here I said the action is trivial, so G1 acting on that is just that. That's why I didn't put it. But in principle, I should put G1 here. Okay, so that's the definition. And then we have that delta squared is 0. That's very easy to check. You should check it, it's fun. And then, because of that, you can define Hn of G with values there. As always, as the kernel of delta, which goes from Cn to Cn plus 1, divided by the image of delta, which goes from Cn minus 1 to Cn. So let's look here. So as I said, for example, for n equal to 2, as I said, if you take omega in C2, then delta omega, which depends on G1, G2, G3, will be equal to 0 if you're in the cohomology, you're in H2, you're in kernel of delta, and that equation is exactly the first box here. That first thing. And now what's the second one? It should be defined up to the image of delta. So I should look at what is the image of a 1 chain. Let's just compute this. Let's say that lambda is in C1. So lambda is a function of 1 group element. What is delta lambda? Now it's a 2 chain, so it depends on 2 things, on G1 and G2. And let's use again the train formula. So it's lambda evaluated on G2 minus lambda. Now G1 enters, so G1, G2, and then G2 exits. You see that's exactly the other equation. I said that omega is equivalent to omega plus the addition of anything like that. That's exactly what I did. So indeed, it seems that this decision has been made to define what a projective representation is, or what an anomaly is. Quite nice. Any question on this? Yes.
But in the last term in your boxed equation, shouldn't it be gn plus 1? By your rule?
Yeah. No, now n plus 1 is kicked out of the train at the end. Right. You can see here also that at the end there is no longer G3.
Does it act on the, well,
No.
in the case?
No, it acts only on the first one. Any other question? Okay. So that's nice. This is, I wanted to say something before the question. Okay. I wanted to say one thing, which you might find helpful if you try to read the literature on this. Some people like to talk about classifying space. So it's kind of a monstrous thing. If you don't like topology. So if you have a group, there is a thing called BG. I will not try to define. But that's a topological space, very complicated one in general. And what's the point? Then some people like to write Hn of BG, with value in something else, say the same ID. That's just the same as H of G. So you can forget about it.
What is BG? I missed the starting point.
Yeah, I didn't say what BG is. It's a very complicated thing. I say you can forget about it, so you don't need it. But I mention it because in many papers you will see this instead of this. Why are there these two definitions? It's just a matter of definition. Hn here is the standard homology, cohomology. Cohomology, we defined it the first time. It's defined for topological space. This Hn is not the same. It's called group cohomology. This I should really call group cohomology. You see, G is not necessarily a topological space with notion of continuity, and so it's just a group. And the point is, you can find for any group, you can find a topological space BG, which is such that the normal cohomology on this BG is the same as this definition of group cohomology. But usually this is useless because, unless you know a lot about direct topology, because this space is so intractable that you cannot really use that anyway. So I just mention it because you might find some statement that I made in contradiction with the literature because of this V, but you can just forget it.
This means drawing simplexes and things like that.
Yeah. So if there is an explicit construction, but it's really not helpful. Okay. It will be super infinite dimensional and so on, even for it. Good. We won't need it. So actually, because of one other reason I mentioned this is, cohomology of simple spaces, like you take torus or sphere, it's quite easy to understand. You can use the RAM cohomology. Those things, much harder. As I said, this BG, no hope to understand it. So you might think, okay, but it's fine. If G is a finite group, I have a working definition here, maybe I can just compute them. But that's also quite fun, actually, in general. So I wanted, in order to prepare for this, actually, I wanted to list some examples, and then I found this book. There is a book that computes, it's a book about group cohomology, and then it has an appendix section, which is, I think, 300 pages long, which computes these for all groups of order which divides 64, I think. So all the groups of order 2, 4, 8, 16, 32, and 64. And that takes 300 pages, just the result to state them, because it's there are a lot of groups, and there's just no way of easily saying what it is, even for these simple finite groups, which are just multiple of 2. So it's not that trivial to compute. So let me just write the other examples that we will need. So examples. So also, should make this comment often. I still make it now. It's quite, now there is all the AI, so you can use ChatGPT or other equivalent things to help you doing a lot of things. So I try to ask ChatGPT, compute group cohomology for some very easy groups like Z2, Z3. And then it very confidently says answers and proofs and so on. And this was all wrong. So even the most advanced version, so you should be very careful. And then you ask, but I thought, I read in another book that this was another result. And then it says, no, here's the proof and so on. So it's quite, it's one of these corners where you should be very careful. So I think this is correct. Hn of G. And again, that's the only thing that we will need for these lectures, but we will need them, so let's record them. So I take a group G, not any group. I take G equals either Z, so I cannot put N, it is P, It's not a prime number. The n, or U1.
So we R of a 2πt, not C of a 2πt, right?
Thank you. So if G is a cyclic group or U1, then you can compute it. It's quite easy. And so if n is 0, okay, that's kind of trivial. H0 is just the functions of nothing into this. Okay, that's the result. Nothing to say. And then the non-trivial thing is that you find G if n is odd. And then you find nothing if n is even. So in particular, you see that if your group is Zn or U1, H2 is always 0. You can never have an anomaly in quantum mechanics with a group which is Zn or U1. Of course, sometimes so does it mean that we never have anomalies in quantum mechanics? Well, no, we should have some, otherwise this discussion would be quite empty. So let me give another example. That's number one. Number two is Z2 times Z2. And now the result is, well, of course, still this one equals to 0. And now for n odd, we have n plus 3 over 2. And for n even, we have n over 2. So it grows in quite a weird fashion. The h1 is z2 squared, and h3 is z to the 1, and 3, 2, 4, 3 grows. But in particular, h2 of z2 is z2. So there is a non-trivial possibility for an anomaly in quantum mechanics if you have a symmetry group which is 2 factors of z2. But 1 is nothing. Okay, so I think that's all. Are there any questions? Don't ask me how to compute this.
The English book, what is the name of what?
The book with the huge appendices. I don't remember the title, but I can find it. It's not the best place to look for it, because even if you want to look for this particular result, well, you don't find it because Cn is not of the 64 in general, so it's a good look for.
But if you specify to n equal to 2, is it in general tricky to compute this?
Just H2. It's probably easier than the general thing, but yeah, I don't know. I didn't really. Maybe someone knows here. There is a tool with spectral sequences and so on, but in practice, if G is a I don't know what group you want, like symmetric group, and you want to move the H2. Maybe someone knows. Not easy in general. Okay, but we will need only this for all of these. So let's now move on. Yeah, so I said that is still here before. So we end at 15 past. It's okay. Fine.
20 past.
20. But I'm very, very slow. So let's just do some examples. E equal to 1. And then we have to move to higher dimensions. So 2 examples. One of them is we discussed it after one of the lectures. I think it's so trivial, but I think it's nice to present it. You can take the 2 quantum mechanics. Well, it's a qubit. What is a qubit? It's a Hilbert space, which is C2, 2-dimensional Hilbert space. And well, if I want to specify a quantum system, I have to say what the Hamiltonian is, and I take it to be 0. So that's almost the simplest system you can have on Earth. Simpler one is one-dimensional Hilbert space. That one has no anomaly, but that one has an anomaly already. So what's going on here? Well, there is a symmetry that acts. If you want to find a symmetry, you need to find what I erased now, but you look at all operators of the theory, and then you look at what acts faithfully on them, and then you find that there is a symmetry group which is SO3. Why is it SO3 and not SU2? But it's SO3 because the operators, they transform in the adjoint representation of the group whose Lie algebra would be SU2, and that's SO3. In other words, just in spin 1. So that on operators. Operators, of course, are all of U2, so Pauli matrices and so on. But then, of course, SO3 does not act on C2. It acts projectively. SO3 acts projectively on C2. Equivalently, we can find a central extension of SO3 which acts non-projectively. There's a central extension which is SU2, which acts on C2 via a representation, non-projective. These are all quite trivial statements, but you see there is this appearance of central extension, and yeah, one thing I didn't mention, I mention it now, is that H2 that's a general fact I could have put in my general discussion of group cohomology, but H2 of G, and in general, let's put A. So A is some abelian group. This classifies the central extension of G by A. So if you have a group and you want to know all the possible extensions by adding one scalar, one element of U1 if you want, the explanation of this thing. If you want to find all extensions of G by U1, this is classified by H2. And indeed, H2 of SO3, this will be equal to Z2. The reason for that is that within SO3, actually you can forget almost everything in SO3. The only thing that matters is that within SO3, there is O2. And within O2 is contains the Z2 factor, and then SO2. SO2 is just a circle, it's a U1, and in this U1 there is another Z2. So that contains two Z2 factors. And the second group cohomology of that part is what generates the group cohomology. So this example is actually what is responsible for the anomaly in the qubit. So maybe you complain about this example because you say it's too trivial. I don't care that the symmetry is SO3 and not SU2. This is too simple for me. So then you can also find other examples. But the point is, so one very important example here is that if you have an anomaly, if you have the group that only projectively, then it means that at least the Hilbert space cannot be one-dimensional. So if you have a theory in which you have an anomaly, and the anomaly is preserved, you cannot change it. It's a quantized thing, as you see all those groups. Quantized thing. Then it guarantees that the Hilbert space is at least of a certain dimension. And so there are some some. It can, for instance, enforce to have certain degeneracy of levels in certain quantum mechanics systems. But yeah, just mention this other
Just to stupid O2 with rotations in the plane. So like
rotations and reflections.
and reflection.
It is O2. That's it. SO2 is just rotations, and then O2 precisely you add the reflections.
So you have the pi rotation.
There's the pi rotation and there is the flip, and these are the two things which together have an anomaly. Actually, okay. Let me, since you asked, let me discuss one more example. And this is my favorite one. You know by now. It's the compact scalar. So what I wrote before, but now it's d equal to 1. If you remember, we had two symmetries. There was momentum and winding. It was a zero form symmetry, but that one was a b minus 2 form symmetry. Now we plug in d equal to 1, we find minus 1 over here. So what is a minus 1 form symmetry? Well, that's a bit mysterious, so let's try to put on. I don't know if Mathieu is here, but yeah, for that. So we have a minus 1 form symmetry. So what is a background gauge field for that? It's you remember, a background gauge field is a form of 1 degree higher than that thing. So that's a zero form. So it's actually just a number. And so this would be interpreted as a coupling constant. So if you kind of analytically continue what I said before when I wrote the general current for there was a B 0, this thing I will call theta. And if you plug back into the action that I wrote and how it couples exactly indeed as the theta angle. So let me write the actions. And B. If I write just this, I don't write the other B, it's the same. You just find integral of phi plus I over 2 pi. I find this. That's exactly the formula I wrote with d equal to 1. And indeed, that's a theta term. Now, of course, all these integrals and so on, it's a bit overkill to write it with this differential form, so I'm just in one dimension. So if you want, you can replace d phi. Whenever you see d phi, it's just phi dot dt. There's just one parameter, it's time. And you can compute what the Lagrangian is. So S is the integral of some Lagrangian. The Lagrangian is 1/2 of phi dot squared plus theta over 2 pi dot. So this is the Lagrangian for the quantum mechanics that we are considering. And okay, now that you have the Lagrangian, you can compute. You can go to the Hamiltonian formalism, and so and phi of course is still my compact scalar, so it's defined on a circle. Valued on a circle. And okay, I don't want to discuss the whole thing, but the Hamiltonian operator becomes so if we say, okay, if we want to go to Hamiltonian formalism, we can redefine a Q. This is our moment, our position variable. This is just phi, and P is the EL phi dot, and then you find that the Hamiltonian is just 1/2 P minus theta over 2 pi squared. And that's just now the quantum mechanics problem written in Lagrangian. So you just solve the Schrödinger equation, and when there's no potential, so the solutions are just plane waves. There is a solution psi n, which is like e to the I n q for every n, and then the spectrum, which you plug this in here, and then you find that the energy of the nth level is 1/2 of n minus 5 minus 2025. Yes. That's the spectrum. We have solved the theory, and the point is, now you can plot this as a function of theta. Observation that one could make here. First of all, you remember that theta should really be interpreted as our background form, the background gauge field for this transformation. So it is a periodic function. So theta and theta plus 2 pi, that's what we call theta, are the same. From here, it's quite clear. In the action, if you add 2 pi, then it's the usual thing. This is quantized, and in the partition function, it will not matter. From the Hamiltonian perspective, you can check that the Hamiltonian as a function of theta, if you shift theta by 2 pi, it's not the same Hamiltonian, so this is shift, but this is conjugated by a unitary operator. H of theta plus 2 pi is the same as H theta, but conjugate into the I think it's either the IQ and either the minus IQ, or maybe the other. So it's a unitary equivalent thing, and so that's why the spectrum, of course, even though the individual levels depend on theta, it's not invariant when theta shifts by 2 pi, the whole spectrum is invariant. So if you draw it something like this, n equal to 1, something like that. That's the spectrum. For instance, theta equals 0, you have the ground state, and then first excited state 1, and something like that. And then the interesting thing is that here, at theta equals 2 pi, there is the degenerate ground state. This degenerate ground state is very hard in general to have a fully degenerate ground state. You might think it's easy in quantum mechanics to have a degenerate ground state. You just take a potential like this, and then you have, but no, it's not degenerate. The instantaneous split, there is actually only one ground state. To have a perfectly degenerate ground state, usually it's because there is a symmetry. And not any symmetry, it's not enough to have a normal symmetry. It's better to have an anomaly. If you have a symmetry which is anomalous, therefore it has a projective representation, like here, then it needs to have, at low energy, a higher dimensional Hilbert state. So that's what's happening here. At theta equals 2 pi, there is a new symmetry that emerges. What are the symmetries? I put them here. But then there is one more. At theta equals 0 or pi, there is a symmetry which is the flipping of phi. Theta equals 0 or pi. There is another symmetry which is phi goes to minus phi. At any other value, it's not there because this term breaks that symmetry. But because of the equivalence from theta and theta plus 2 pi, at theta equals 2 pi or 0, if you flip phi, you have a symmetry. And so that's a Z2. Zero form symmetry. And the point is that Z2, zero form symmetry, combines with that U1, zero form symmetry, to form an S and O2, zero form symmetry. So that's the symmetry. And then you can ask, how is it realized on the state? And that's very easy because the state, I mean, we have written here. So you can check how it acts when Q goes to minus Q, how it acts when Q goes to Q plus 1. And you can work this out for any value of theta, whether 0 or 2 pi, and you find that at theta equal pi, there's a projective representation, and it's exactly the same as here. This O2 is the same as this O2 here, and this guarantees that the ground state is degenerate. The point of this is, again, this is kind of a trivial thing because we can solve the problem. The point is, in this Hamiltonian, if you add any term, a potential that preserves the symmetry, which means it just, again, the only thing that matters is the Z2, Z2 inside O2, so it should just be invariant under phi goes to minus phi, and phi goes to phi plus pi. Anything that you add which is invariant under that, you're guaranteed by the anomaly that it has a degenerate ground state here, which is the qubit. Any question on this? Then in the last 10 minutes, I want to go to higher dimension and to, well, then the actual new insight from today will be next time. Let me just give a glimpse of it. We have not done our gauging thing that I promised. It will be next time. But to finish, let's so, are there any questions about this? So now we move to, back to general dimension. So now we want to characterize anomalies in general dimension. We have seen that when d equals to 1, the anomaly is characterized by, so now it's just standard quantum mechanics, and then it's this is the fact that representations are projected. And we want to generalize that fact to high dimension. And for this, it's useful to look at the equation here again. If we have this, then we can ask, what is the mathematical nature of Z? Very vague question. And the direction I want to take is the following. We should actually ask what is QFT. I have to go there. I promised at the beginning, the first lecture, that understanding the symmetries would also force us to reconsider what is QFT as a whole. We have all these questions. So the one possible answer here is that a QFT is Z. Z is the thing that completely characterizes the QFT. So one possible answer to this question is, okay, let me first answer the first one. So Z seems to be a complex number up to a phase. I put this in quotation mark because it's vague. And we want to make this a bit more precise. But for that, I need to address the other question. So what is QFT? So very roughly speaking, we can identify it with Z almost. So it's we can say that it's a gadget which does various things. If you have a closed MD, you have a closed manifold MD, such as closed manifold MD. Then you associate to it a number, the partition function on it. So it's Z. And Z associates Z of that thing. Z of the mesh. That's the partition function on that. And what is this? Well, schematically, we just write it this way, is the path integral over all fields of e to the minus s. And the fields are defined on MD. And D up to whatever field they take value in make. Let's say, or you could have more general. So that's the point is you need this to be closed. Otherwise, you don't get a number. If it's not closed, you need to specify what's happening at the boundary. You need to specify boundary condition. If it's not closed, then so you have something like that. Maybe something like that. Then what does D do? Well, you try to do that, and then you find you integrate still d phi e to the minus s. But now the fields phi are all fields defined with some boundary condition. What's happening here at the boundary? So we need to specify that phi at the boundary equal some phi 0. Phi 0 is the field defined on a one-dimensional less thing, the boundary. And so that thing is not a number. It's a function of phi 0. Right? So if you have a non-closed end, then you associate to it not the number, but the function defined on the boundary conditions. To every boundary condition, you can compute the partition function. You need the boundary condition. So that motivates this idea that there is this. You can make these two things compatible by saying that D is a functor from the category of Bordisms. So what is Bordism? Let's put D and D minus 1 over here into, let's say, vex. I'm a bit informal here. So what does this mean? There is a category of Bordism. This is just a category which the objects are the boundaries. So the objects are D minus 1 dimensional manifolds. Let me just denote them. D minus 1 manifolds. And the morphisms are, well, if you have two objects, and D minus 1, then there's another one here, and prime, D minus 1, then the morphisms are D-dimensional manifold, which make a Bordism, which go from one to the other. Again, very vague. Be more precise. So this is and this is the morphism. And now, if you have this, then you can say that what is a functor that goes into vector space? Yeah, so vec is the category of vector spaces. So the objects are vector spaces, and the maps, the morphisms, are just linear maps between vector spaces. And so what's a functor? It's a thing that for each object gives an object here, for each morphism gives a map here, and they should be compatible in the whole class of operations. And okay, so that's a way of saying those things. And now the point is we want to have not any vector space, but typically the spaces here will be some kind of Hilbert space. You know, so in the one-dimensional notation, if I have a one-dimensional manifold, then to a point, I associate the Hilbert space, and then here I have another Hilbert space, and this is the evolution, which is the evolution operator, the linear map between the Hilbert space here and the Hilbert space here. That's the generalization of this in any dimension. Okay. And again, we don't need to understand all the details here. The only thing is, imagine that we have a QFT. So a QFT is such a Z. And now imagine we have such a Z, which to the boundaries associates a vector space which is one-dimensional. Let's imagine that we have this. Then, what is an element of a vector space which is one-dimensional? Just you pick a basis, and then that's just the one number. But there is no canonical way of picking the basis. Right? If you have a one-dimensional vector space, so actually an element of a one-dimensional vector space is exactly a complex number. So these are all the complex number up to a rescaling, because someone else could have picked a different basis. So the idea, and then I have to stop and we will explore the consequences next time, is that that thing here, this is not very precise, but maybe we can replace it by an element of a one-dimensional vector space. And this one-dimensional vector space comes with it's a bit more than a vector space. It's a Hilbert space, so it comes with a length. So different people might not choose the same basis, but the basis will have the same length. There will be, so any two person will pick a different base, but it will be related by unitary transformation, U1 transformation. So that's the case. And so if you see this, then you see that it's kind of it's nice. So you might want to say, okay, then Z evaluated on my manifold is just an element of a one-dimensional vector space. It doesn't work with that, because the elements of the vector spaces, they are associated to D-1 dimensional manifolds in this description. So the idea is next time. So first of all, here I was very, very vague about what these vorticants are, but on these manifolds you can add a lot of structure. So manifold plus whatever structure. For instance, it can be just manifold, but you might want to be orientable, maybe add a metric, maybe add some other fields and so on. Here, nothing, it's just the definition of a topological field theory, but in general, you can have many other things. And here also, you need that guy to have structure. And part of this structure could be a bunch of background fields. And so you see, let's finish with this drawing. Let's go back to our quantum mechanics example, where I had this thing with two insertions, UG1 and UG2. This is a one-dimensional manifold with a certain background. Which background? Well, the fact that there are these two. Then there's another one with UG1, G2. This is kind of the same manifold, but with a different background. Then you might say, here I had Z, which was a particular thing. Here I had the same Z times the phase. Well, you might say that, okay, this was just a vector space in this vector space associated to that in a one more dimensional theory. So you connect those things. Now you have a two-dimensional connected thing. That connecting thing to vortism should have the same structure, so it should also carry the background field from those guys. So those guys should just be the boundary of something which lives in one more dimension and which has to undergo some non-trivial thing in order to accommodate for. So the one more dimensional thing is the interpolation, and it tells you exactly in one more dimension, it tells you what were the topological changes that you needed to make in order for this to happen. And that theory here in the middle, the anomaly theory, is a very, very simple theory because it associates with each boundary a one-dimensional Hilbert space, which means whenever you have this anomaly theory, then you have boundaries. Boundary are just some particular configurations of the background gauge fields, and they are all the same vector space, except there is no particular choice of the basis. Hence, the partition function is just the scalar in front of this non-defined basis vector, and therefore it's either this or the same thing up to a face, and this is determined by how you move. So, okay, I wanted to arrive here to just have this idea on the board. So next time we will start from here. I will repeat all of this, and then at last we can solve our mystery, which is how we can gauge. So next time will be on Friday. No, it is Friday today. It's on Monday, isn't it?
Monday.
It's 3 days.
In the afternoon.
Monday in the afternoon at 2:15. Yeah, so we meet. Any question? I mean, the last part was really rushed, but I wanted to at least show the picture. If you have a question on this, we can maybe answer next time. Are there any questions on the previous things? Yes.
Maybe. Oh, sorry, one thought.
Oh, about it.
No, it's very vague. I'm just thinking. I mean, it seems very abstract if you uplift it like this. I mean, if you want to merge these two cases into one, let's say.
Which two cases? Yeah.
Well, if the manifold is closed or not.
Yes.
I mean, in principle, these are equivalent if I specify or not. Let's say I say.
Yeah. Okay. Yes. Okay. Yeah. Maybe I didn't say that. Here, if it's closed, it means that the boundary is empty. So to the empty boundary, I associate a trivial vector space as well. And so that should be seen as a function from empty to empty. So that's a scalar, if you want. That's so it fits into the. If there is an empty thing, then you have no boundary condition to specify, and then you just.
So maybe asking a bit vaguely, but I guess you'll comment on this next time. But how useful is this abstract generalization if I know what is my manifold?
Well, it's useful to understand. Okay, here, for instance, we can understand that the anomaly, the idea would be that here you can make any kind of topological manipulation. So, for instance, here there is the anomaly, and then you can absorb this anomaly into another action that you write here, and that action exactly compensates it. So it's here, for instance, there is this factor omega, but then if you say that this thing, so now omega kind of resides here, formally you can absorb the anomaly with that. And okay, it's just a formal trick. You might question, and my question, what's the point for all of this? But then the point is after we gauge. So when we gauge, some of these things will become real. Some of those things will be, here it's all very small dimensional, but you should imagine that here you have a 4-dimensional thing with a lot of stuff happening. Here you have 5-dimensional thing in which the anomaly is happening. And then some of the things that we will draw here, after we gauge, will be pushed here. And so this means that for the first time, we will need to extend once more our definition of symmetry. Up to now, our definition of symmetry was this, and they merge into this for group law. But after we gauge, we will see that this will no longer hold. We will need to incorporate what's happening when we have those kind of things, which are now. And so this will induce the mixing between different higher form symmetries. So, and this happens, yeah. And I will start with the example probably next time. But for instance, if you just take U1 gauge theory with chiral with a bunch of fermions, for instance, spinors, light spinors. It's high, but you have the left and the right. You have many. Then you take n of them. Then there is an SUN. This is the flavor symmetry that rotates your, let's say, the quarks or the electrons. This is zero form symmetry. And then there is the one form symmetry that comes from the center up here, right, that we saw. technically the magnetic, one from symmetry, one. And then those two things, they mix in a particular way. There will be an anomaly there. But this is after you have gauged that. So actually the anomaly initially comes from here. Now we have gauged. So now it means that those two things, they are both global symmetries, but now they will interact in a certain way. And that way will be exactly the same as those drawings, but now drawn in real space. And so that's the example that we will discuss next time. So that's called the Suku. So it's not just formal, I mean, it's still formal. Now, at least it's not in the one more dimension. It will happen in the real D-dimension. More question? Okay, so then continue on Monday.